Welcome to the Crazy Hat Chemist. So another video here on equilibrium. So let's get started. Bam! So today we are talking about equilibrium calculation number 3. Okay, so we have 1 mole of each hydrogen and iodine. They're placed in a 1 liter flask. We're going to calculate the equilibrium concentrations of all reactants, that's the hydrogen and the iodine, and the product, that's the hydrogen iodide, knowing the Keq value of 55.3. Now before we get started, I want you to make sure that you understand the 55.3. Since that value is greater than 1, we know that this reaction is product favored because it's greater than 1 for the K value. Alright, so here's the balanced equation. That is hydrogen gas, which is of course diatomic, plus iodine gas, which is of course diatomic. Got the double-headed arrows there to let me know that this is an equilibrium reaction. Will produce 2 moles of hydrogen iodide, which is a gas. Now everything here is a gas, so that means that they're all involved in the Keq expression. So that's great. So what we need to do is we need to look, I got 1 mole of hydrogen, 1 mole of iodine, and that is in a 1 liter flask. So in order to do this problem, we're going to do something that we have done before, and that is work with an ice table. Okay, ice, ice, babies. Okay, here we go. Initial, change, and equilibrium. That's what ice is representing here. Okay, so what's the initial concentration of the hydrogen gas and the iodine gas? Well, it's 1 mole divided by 1 liter, so it's 1 molar. Okay, so it's 1.00 molar for both of those. How much do you have on the product side? Well, always with every single ice table, except for one special example that we haven't talked about yet, but always for these examples we have nothing on the product side because we are assuming that we haven't actually started the reaction. So initially, at the very beginning, there is nothing on the product side, and that's why there is a 0 for the hydrogen iodide. Now, we need to figure out what the change is. Now, remember that reactants always have a negative sign in front of it, and products have a positive sign in front of it. The reason for the negative sign is that reactants are decreasing over time, and the reason that the positive sign for the products is that they are increasing over time. So hopefully that makes sense. Then we're going to look at the stoichiometric coefficients that are on the balanced equation. So in front of the hydrogen is a 1. In front of the iodine is a 1. So that's why it's going to be 1x for each of those and a minus in front of each of them because they are reactants. So I got a 1x in front here for the hydrogen, and I got a 1x for the iodine. There's a 1 coefficient in front of that. Hopefully you see that. It's invisible. All right, now on the product side, we have 2 moles. So it's going to be a 2x. And since it's on the product side, it's going to be a positive, and because they increase over time. Okay? All right, now what we're going to do is we're going to take our initial column, or our initial row there, period, and our change period, and we're going to add those 2 columns up for each of those either elements or compound, and we're going to get the equilibrium. So that's 1 minus the x, 1 minus the x, and 0 plus the 2x is just 2x. So what's important in doing the ice table is figuring out what these values are. So the next thing that we need to do is we need to write the Keq expression. That is products over reactants with the stoichiometric coefficients as exponents. Solids and liquids are not included. So here's the Keq expression right here. That's hydrogen iodide in the numerator to the power of 2, that's the exponent, divided by hydrogen and divided by iodine to the power of 1 for each of those. Now, you're given a value of the Keq of 55.3, and I mentioned earlier that this is product favored since it's greater than 1. So we're going to plug in the Keq value, and then we're also going to plug in the equilibrium values. Okay, so we're going to do that in just a moment. Hey, by the way, I do have a great joke, so don't forget to watch the end of this video to hang on for the great elemental joke. All right, so we're going to plug in those values. Here we go. So we've plugged in the Keq value, we've plugged in the 2x, and its quantity squared, right? And we plugged in for the hydrogen and the iodine as 1.00 minus x for each of those. Now, if you see this, we can do a little simplification just in the denominator. So I want to focus on just the denominator term. I got 1 minus x times 1 minus x. What is that equal to? Well, that's equal to 1 minus x to the power of 2. So that's squared. That's a squared term. So this seems like a complicated problem to solve, but I got 2 squared terms on the right-hand side of this. So what are we going to do? We're going to take the square root of both sides, and I will get rid of the squared term. So I'm going to take the square root of the left-hand side and the right-hand side, and that's what I'm going to get right here. So I'm going to take the square root of both sides. What that effectively does is on the right-hand side get rid of the squared terms, and I'm just going to have the 2x in the numerator, the 1 minus x in the denominator, and then whatever the value is for the 55.3, the square root of that. So here are those values right here. So the square root of 55.3 is 7.436. That's going to equal 2x divided by the 1 minus x. Now, we're going to solve for x. That's all we're doing here. So we're going to cross multiply, if you will, and this is what I get. So I got 7.436 times the quantity of 1 minus x is equal to 2x. We're going to distribute the 7.436 over the 1 and the minus x respectively, and that's what we get right there. Now what we're going to do is we're going to move that x term, which is the 7.436x, to the other side where the 2x is with an addition, and that's what we get here. Now I have my non-x term on the left-hand side and my x term on the right-hand side. I'm going to divide by the stoichiometric coefficient in front of the x, which is the 9.436. And I'm going to get this value. So this value is 0.788. Now, what is this? Well, if I look back in the oval equilibrium portion here, I don't see an x here at all by itself. I see a 1 minus x and I see a 2x. So what I have to do in order to solve for the hydrogen concentration, I'm going to plug in this value for x into that equation at equilibrium. So that equilibrium is 1 minus 0.788. I'm going to do the same thing with the iodine at 1.00 minus x, which is 1.00 minus 0.788. And that's what I get right here. So the hydrogen concentration is equal to the iodine concentration, which is equal to 1.00 minus x. I'm going to plug in that x value, and I'm going to get 0.212 molar. Okay. All right, now I'm going to do the same thing with the hydrogen iodide, the product, except for this time it's equal to 2x. So I'm going to take that 0.788 and multiply it by 2, and I'm going to get the hydrogen iodide concentration, and that's 1.58 molar. All right, you should be able to plug in these values back into the equilibrium constant expression and obtain a value for the Keq that's very close to 55.3. Now there is some rounding here along this whole process, so it might not equal exactly 55.3, but it should be very, very close and not far away. That is actually the check in which you should be doing. You should be plugging in the hydrogen concentration, the iodine concentration at 0.212 molar, and the hydrogen iodide concentration at 1.58. Square that, divide it, and then get a value of the supposed Keq, because you have reached this equilibrium and it should be close to 55.3. If it's not, then you need to redo the problem because you have made some kind of math error. So here is my elemental humor, and I'm going to start off with my crazy hat here. Elise, thank you very much for this beautiful hat. Your father and you gave me this hat, and I truly appreciate this hat, so thank you very much. So here's some elemental humor for you. What weapon can you make from the elements of nickel, iron, and potassium? Not in that order. Think about it. What weapon can you make with nickel, iron, and potassium? Not in that order. It's elemental humor, so we need to be looking at the periodic table and those particular elements, and of course that would be a knife, and here is a knife for you. Okay? All right, so I am the Crazy Hat Chemist. Give me a thumbs up if you like that video. Subscribe to my YouTube channel and find me on the web. I got a great website set up that my son did. I'm going to see you next time for more cool chemistry videos. Talk to you later. Bye for now.